Alrighty, so we are continuing to rationalize the denominator. Again, that means we don't want a radical to be left in the denominator or a fraction left in the radical. So if we look at this problem right here, we're going to need to make a list of all the perfect cubes. So we could keep going, but I at least listed 4 of them. So 2 times 2 times 2 is 8, 3 times 3 times 3 is 27. These are all perfect cubes. So we need to multiply this denominator by something such that it will make one of these numbers in the list. So for example, 2 times 4 is going to make this 8 here. So that's how I know to pick 8, because that 2 can go into 8. So now that I know to put a 4 there, I'm going to put a 4 up here as well. So then we'd have 5 times the cube root of 4 over the cube root of 8. So again, the whole reason I put that 4 there is because now it will make this, and the cube root of 8 is 2. What times itself 3 times is 8? That's 2. And then if we look at this and we ignore the radical, you cannot simplify 5 halves, so that is our final answer. So I'm going to do this problem again, but instead I'm not going to pick 8, which I would because it's smaller. This time I'm going to pick 64, because can't 2 go into 64 as well, this 2? So both of them would work, but I like 8 the way we did it the first way because it's smaller. But I'm going to redo it and now pick 64. Okay, so if we pick 64, 2 goes into 64 32 times. So we're going to put a 32 here. And then we'd have 5 times the cube root of 32 in the numerator. And then we'd have the cube root of 2 times 32 is 64. And the whole purpose of doing this is because now the cube root of 64, what times itself 3 times is 64 is 4. Now we have removed the radical from the denominator. But because we didn't pick 8, which is smaller, now this problem here is going to be able to be simplified. So if I take my 32, let's say I make a factor tree. Okay, there's my factor tree. Let's make the jail. Now remember, there's a 5 already here on the outside. There's already that 5. Let's make my little jail thing here. And I need a group of 3. So our index here is 3 in this problem. So 1, 2, 3. So they escape the jail, the radical jail, but only one of them survives. And then these 2 here, they don't have another partner to make 3. So you have a 2 and a 2 in the inside. Well, 2 times 2 is 4. So we would have 10 cube root of 4 in the numerator, and then we have this 4 in the denominator. So now we can simplify right here. 10/4, we can divide them both by 2. And we would get 5 cube root of 4 over 2, which is exactly what we got when we used 8, which was easier. We didn't have to do this last part, the simplifying part, because we picked the smaller number. Alright, let's take a look at this problem here. So I have this radical in the denominator. I don't want it there. So I need to think of what cube root to multiply it to, numerator and the denominator. So I need to think of which number I can multiply 9 with something that will make one of these numbers in the list. So 27, for example, would work. So 9 times 3 is 27. So then I would put a 3 here. And then I would have 3 cube root of 3 over the cube root of 27. And the whole reason for doing this is because now the cube root of 27 evaluates to 3. And we have rationalized. Then we're going to take the 3 and the 3 because it's not in a radical. And 3 goes into 3 once, 3 goes into 3 once. So we're just left with 3 rad 3, or the cube root of 3. If you write your answer with a 1 there, it is not wrong, but it is not necessary, because 1 times anything is itself. Okay, so if we look at this problem, I see that the index are both 4. So if we join them, that doesn't do anything. So we try that. Not going to do that. So then I'm left, then the only other thing I can do is, I have a radical left in the denominator. So we need to think of something to multiply the 4th root of 2 by. And whatever that is, we have to also do in the numerator so that it doesn't change the original value. So since the index is 4, we need to make a list over here. And we could keep going, but that's good enough. And I need to think of which of these numbers can 2 go into. So 2 can go into 256, but that's a big number. Why not choose 16 over here? So that's how I know to pick this one. And 2 times 8 would make 16. So that's how I know what to multiply the original fraction by. So now I have 5 times 8 is 40. And then we have the 4th root of 16. And the whole purpose of doing this is to make it the 4th root of 16, because what times itself 4 times is 16 is 2. So now we have this. And I could take the 6 and the 2 because they are not in a radical, and I can simplify it. 2 goes into 2 once, and 2 can go into 6 3 times. So now I have this. And before I say I'm done, I just got to make sure. I got to make sure that this 40 can't be simplified. So because this index is high, I'm going to make a factor tree instead of using method 1. So I have made the factor tree, and because this index here is 4, I'm looking for a group of 4. 1, 2, 3, not enough. So this is it. Cannot simplify that further. So our answer is 3 times the 4th root of 40. Alright, let's take a look here. So we don't want this radical left in the denominator, so we need to make a list with our perfect cubes here. And we need to pick which one that 3 can go into. So 3 cannot go into 8, so we're not going to pick 8. But 3 can go into 27. So we need to multiply by the cube root of, so 3 times 9. 3 times 9 would make 27. Okay, but 3 does not go into 1. So 3 doesn't go into 1, 3 doesn't go into 2, but 3 does go into 3. So that's how I know here that I want this to be a 2, because 1 plus 2 would make 3 as the exponent, and then the index 3 right here can go into it. So that is how I pick out my 9x squared there. So I'm going to multiply that to the numerator as well. Now keep in mind that 3 also can go into 6, but the reason why I don't want to pick 6 is because I have an x here. Remember, it's a cube root, so I already have an x there. I just need these two to join it, so that they can escape the jail. If I pick 6, which is totally cool, 1, 2, 3, 4, 5, 6. So if I put and change this to x to the 5th, that's fine. But I'm going to have, because I picked something bigger, I'm going to have simplifying to do at the end. So 6 works because then I would have 1, 2, they would all escape. So I can put x to the 5th power there. But then I'm going to have more simplifying at the end. So that's why I'm going to go with 3, because 3 can go into 3. So I'm going to make this a 2. So now I'm going to multiply straight across. 2 times 3, or the cube root of 9x squared. And then we have the cube root of 3 times 9 is 27. And if I have an x and then I have 2 more, that's x cubed. Now the whole purpose of doing this is so that now I can take this and the radical will be gone, because the cube root of 27 is 3, and 3 goes into 3 once. So now we're left with this. And now I take the 2 and the 3x and ask myself, can that be simplified? No. And then if I do a factor tree for this 9, I don't have enough to escape this jail because the index is a 3, and 3 can't go into 2. So it is completely simplified. And that is our final answer.